Hello everyone, I am Ankita Shi from Electronics and Communication Engineering Department. Today I am going to demonstrate experiment 4, uniform quantization and pulse code modulation using Python. The objective of this experiment is to understand how an analog signal is quantized and encoded into binary form, and to study the effect of increasing the number of quantization bits on the signal to quantization noise ratio or SQNR. First, I import the required libraries. NumPy is used for numerical and mathematical operations, while Matplotlib is used to plot the graphs for visualizing the signals. Next, I generate the original analog signal. Here the sampling frequency is set to 1000 Hz, meaning 1000 samples are taken every second. The signal frequency is 5 Hz, so the sine wave completes 5 cycles in 1 second. The variable t represents time and x stores the normalized sine wave whose amplitude varies from -1 to +1. Instead of testing only one quantizer, I test 5 different bit resolution: 2, 3, 4, 6 and 8 bits. This helps compare how increasing the number of bits improves signal quality. This loop repeats the complete PCM process for each bit value. The number of quantization levels is calculated as 2 raised to the power n. For example, 2 bits provide 4 levels, 3 bits provide 8 levels, and 8 bits provide 256 levels. Since the signal ranges from -1 to +1, the total amplitude range is 2. Dividing this range by the number of levels gives the quantization step size. The signal values are shifted from the range -1 to +1 into 0 to 2. Then each value is divided by the step size and rounded down using the float function. This assigns every sample to a quantization level. The cliff function ensures that every index remains within the valid range from 0 to L minus 1. This prevents invalid indices. This line converts the quantization index back into an amplitude value by taking the midpoint of each quantization interval. The resulting signal is the quantized signal. The difference between the original signal and the quantized signal is called the quantization error. The mean square error measures the average power of the quantization error. A smaller MSE indicates better signal quality. This calculates the average power of the original signal. SQNR stands for signal to quantization noise ratio. It compares the signal power with the noise power. A higher SQNR means less quantization noise and better signal quality. This formula gives the theoretical SQNR for an ideal uniform quantizer. It shows that every additional bit increases the SQNR by approximately 6 decibels. Each quantization level is converted into an n-bit binary code. These binary codes are the PCM output and represent the digital version of the analog signal. This graph compares the original analog signal with the quantized signal. The blue curve is the original sine wave, while the red staircase curve is the quantized signal. The staircase shape appears because the amplitude is restricted to fixed levels. As the number of beats increases, the staircase becomes smoother and follows the original signal more closely. Staircase characteristic. This graph shows the input-output characteristics of the quantizer. The x-axis represents the input signal and the y-axis represents the quantized output. The staircase pattern demonstrates that a range of input values maps to the same output level. Increasing the number of beats increases the number of steps, making the approximation more accurate. Quantization error. This graph shows the quantization error over time. The error is simply the difference between the original signal and the quantized signal. Notice that the error remains very small. As the number of beats increase, the error decreases because the quantized signal becomes closer to the original signal. Error histogram. This histogram shows how the quantization errors are distributed. Most errors are concentrated around 0, indicating that the quantizer introduces only small errors. With higher bit resolution, the histogram becomes narrower because the errors become even smaller. SQNR versus number of beats. This graph compares the measured SQNR with the theoretical SQNR. As the number of beats increases, both curves increase almost linearly. This confirms that increasing the bit resolution reduces quantization noise and improves signal quality. The measured values are very close to the theoretical values, which validates the experiment. In this experiment, I successfully implemented uniform quantization and PCM using Python. I observed that increasing the number of quantization bits increases the number of quantization levels, reduces the quantization error, decreases the mean square error, and improves the signal to quantization noise ratio. The measured SQNR closely matches the theoretical SQNR, confirming the correctness of the implementation. Thank you.